Very good morning to all of you. Maybe we can start now. So first of all, I welcome you all for this webinar. And today this webinar on data and data quality in mineral inventory estimation, I'll be presenting along with Vikas, uh, who is also here, senior principal geologist here in Datacode. So to start with, so this is us, myself and Vikas. We both work in Datacode right now. A little bit about housekeeping. So all attendees are on mute and are requested to keep on mute. If you have any questions, please enter it in the chat box. If you are experiencing any technical glitch or any problem, then please try exiting and rejoining the webinar, and hopefully it will work. A disclaimer, the presentation is for informational purposes only and should not be used and considered as professional advice or a professional service, although Datacode is always willing to engage with clients on specific situations. A little bit about Datacode. Datacode is a leading organization in the field of geoscience industries, bringing cutting edge technology and services to the industry, specifically to the growing Indian market for over 25 years. And we have international business associates and partners working with us. And we believe in the mantra of 3 E's, which is empowerment of end users, enhancement of employees' skill sets, and equity to all stakeholders. Coming to today's topic, before that, I'll switch off my camera so that there is no hassle or problem while presenting. So I switched off my camera. So coming back to today's topic. So today's topic is on data and data quality, and a little bit of an overview of what we are going to cover today is actually the topics we are going to cover today are resource estimation processes, data collection, data validation, implication of data quality, numeric data for mineral inventory estimation, concerns regarding any data quality, errors which are there in classification and terminologies, and sampling. We'll try to understand sampling patterns as well. And lastly, we'll summarize all the topics or all the lecture points which we will be covering today. Now I'll hand over to, so Vikas will start the presentation with starting with estimation process flow. So over to you, Vikas.
Thank you, Dhruv. Good morning all once again. So let us just understand the resource estimation process. So today basically we'll be talking more on data, how the data are collected, what's the role it plays in resource estimation process. So as we understand the resource estimation process, the first step is data collection. And then we move on to geological ore body modeling, and later on, basically in the data collection, there is mapping data, drilling data, logging, sampling, assaying, QAQC, all the data, all different types of data that are collected. Later on, as we move, there is whatever the data is collected, we do interpretation of that, the geological interpretation, the delineation of resource model. So we get the model, and later on there is exploratory data analysis, wherein we apply all geostatistics analysis, and then we go on to resource estimation, where the assessment of resource is done, and based on that resource classification is done, wherein we define the reserves and resource, and later on we move on to resource reporting. It can be in different formats. It can be JOG, SAMREC, or Canadian NI 403. The basic reason of defining this is, as you can see, the data collection itself takes about 50% of the process. So the most important part in the entire resource estimation process is data collection, wherein you spend about 50%. Later on, the modeling part might take 20%, exploratory another 15%, estimation 10%, classification 5%. So basically, the today's presentation is more about data collection and how pivotal, how important it is in the entire estimation process. So moving to the next slide, data collection. So as I said, collecting data, it can be in different types. It can be the basic mapping data when we go to the field. So different points are collected, samples are collected. Later on, drilling is done. Based on drilling, you get core samples are logged, and later on they are analyzed, they are assayed. Whatever the assay values that you get, you do a proper QA/QC, that is quality analysis and quality control, which also plays a very important role. Without QA/QC, there is no point in moving forward with the data. And later on, after that, you do density. Density also plays a very important role, because based on that, the tonnage is calculated. And so that forms the entire data collection process. So all this data goes into the resource estimation part. So basically, whatever data is collected, so there has to be a proper chain of custody. This is very important, because once the data is collected, it is sent, once it is logged and sampled and assayed, it might be transported, it goes to laboratory. After laboratory, there might be crushing, pulverizing, everything, and after that, it might go for analytical. After analytical, you get the assay. So, like if you are giving a nomenclature for a borole sample, so it has to be decided at the data collection step itself, so that whatever the sample ID that you give at the data collection point, it is being incorporated in the database, which is used before estimation and also during before reporting. So it plays a very important role. So the chain of custody is very important, and even when you are giving, you have to have a proper document in place, so that many times what happens, that the data that you have given, and during estimation there might be some error, and you might want to go back and check that data again. So for that, you need to trace the data, and for that tracing of data, all this chain of custody is required. Otherwise, you might not know where the data came from, which borole it came from, or where the residue was, where the pulp was. So this helps, and this is the best practice that has to be employed by every exploration company and anyone who's doing resource estimation. So size of sample. So as you can see, we have put two photographs. One is of drilling rig and one is of a teaspoon, wherein there is just a teaspoon of sample. So the samples that are generated in drilling, so that might be drilling core. So the drilling core, sometimes we sample like maybe for a homogeneous of 3-meter core if you get, or 1-meter core if you get, the samples are of in kgs, the quantity. It might be sometimes 10 kg, 5 kg, 3 kg. The entire sample is later on crushed. After crushing, no, before crushing, it has been splitted by core cutter. Then it is crushed, and then they are pulverized. And after pulverized, the samples which is used for assay is hardly 10 to 15 grams. So you can, here you can see the samples which was more than 10 kg has been brought in up to 10 to 15 gram, which is analyzed and assayed, and that value, the assay value of just 10 to 15 gram is used to to incorporate the entire lithology what was encountered. That's why the size of sample is also very important, and also the entire homogeneous part, the sample has to be properly homogenized, and it has to be properly quality controlled, because a very small portion is used to do the assay. And coming to data validation. So data validation plays a very important role in estimation. Basically, it is a process of ensuring data, which it has underground data cleansing to ensure that they are both correct and useful. Basically, it assesses the integrity of the information. What are the advantages? A clean data, it is used for reliable information. Non-validated data, it might play a question on the validity of the entire estimation, whether the estimation is correct or not. So only once the data is validated, you can say the data is clean, and it has direct influence of resource classification. Basically, around 7 50 to 80% of the resource estimation is taken care by data validation. So data validation also plays as I said, the data collection plays a 50% of entire resource estimation part. So similarly, around 70 to 80% of resource estimation is done during data validation. Then coming to no, just let me just, there are some key points which you have to consider for data validation. You have to treat it very carefully, and there can be errors while capturing this phase. So you should have the ability to read the data. So what is there in reading the data? As you can see, the numbers, you have to see if the numbers make any sense. So whenever the number that you put for the database, it has to come in a proper format. So with the number itself, you should be able to trace from which borrow it came from, and even when it's the sample, it has to correlate with that. So the sample, the initial part, that's why I had said naming the number and sample comes in the initial part itself, which can go on till the end process. Second, reading the data should be like extraordinary large or small values. Many times it happens that the assay value or that you get, it might be very large. It might be in the order of 10, but you might be it might be in the order of 100, but you might be expecting something in the order of 10. So you should be able to read this so that you find out any anomaly in the database. You have to look for errors in the data files. So many times you have to check whether the data is readable or not. Otherwise, if the data is not readable, it might, if it is in some other format, you might have some error. And there can be duplication of information. So many times, if there is some missing data, you might write -9 or -99. So you have to do it. This nomenclature has to be done it properly. Also, you need to make sure consistent values for missing values. So many times you don't have some assay values. So you should never replace them with 0, because what happens once you mention it as 0, the data, the software might consider it as 0 value. So when you go to average out the entire while doing geostatistics, it might come out that that portion has 0 values, but in actual the data might have been missing from there. So you must be very careful while mentioning these values. So again coming to convention which I have been mentioning, see DD91/02, DD91/02, and DD91-02. These all are the same numbers but in different formats. So you have to be very careful which number you are using, because the same number you will be using till the end of the project. So even a forward slash or a backward slash or a dash can make the data unreadable, or that sample might be missing from the data if you don't use those properly. And there can be some overlapping samples. Many times it happens that you break, if there is a change in lithology, it might end somewhere in between 99.5, 99.2. So you need to even mention those depth properly so that the overlapping sample is not missed out, and there is a proper flow of data. And also, yeah, yeah. So coming to implications of data quality, this estimated, they are basically derived from representative samples or logs. So this data is, as I said, it is applied to a large volume, entire mass process. As I said, the entire core might be of 3 or 5 meters, which, and finally the sample that is assayed is just 10-15 grams. So you have to be very careful with that. And the entire volumes are in, like, it's in very large number. It might be in million of times. So when the tonnage is reported, we report in million numbers. It is extrapolated. So that's why this data plays a very important role. So the raw data plays a very important role, and it has to be of very high quality in this entire process. Just to understand difference between samples and specimens, samples are the continuous, are the, like for core, you will call them samples because they are continuous in nature. Specimens can be a grab sample or any geological sample. So you need to understand which are samples and which are specimens. Specimens are very much useful maybe for reconnaissance survey and initially for generating targets. But for resource estimation, you require samples which are continuous in nature. So what are the errors that happens in sampling? Basically, there are many errors which have been reported. So deliberate errors they are not acceptable even as per the reporting standards. So there are many illegal activities which are carried out. So there are some of the examples I can say, like for sorting as an example. There was a diamond hoax which was in the year of 1872, wherein a false, it was an American project. They falsified a diamond deposit, and based on that, there was a huge craze of exploring diamond in that project. But later on, it proved to be a false data, wherein the sample was tampered, and they had purposefully made it so that they could get benefits. Similarly, Brex 1993, like it was a group of companies. So for gold mining, uh, they had purposely increased the data, and it was basically a trading. They were listed, and it was a penny stock. It went on increasing its share price, and later on, somewhere this happened in 1993. Somewhere in 1987, they came to know all the data which was there was all false, and that's how later the company collapsed. Even the share collapsed, and I can say this happened in 1993, and only after this NI 43101 in Canada, this was brought into force to protect the investors from all these falsified, all these data, all the false information. Similarly, importing mineralized material. Many times it happens that a drilling is being done. So what the drillers might do, they might, if at all they are not getting good recovery, or even if they have been told, they might get core from some other project and they might put into their core box. Even this has to be checked so that you know where the core is coming from and the data is not falsified. Similarly, falsification of historic documents. Many times it happens, whatever the historic documents are there, they have been changed so that to meet your current requirement, they will change all the data. So all these things has to be kept in check. So what are the means of minimizing these errors? You have to do a proper technical verification of the old historic literature, all the legacy data. It has to be verified. You have to carry independent sampling, and also the whatever the samples which are there, it has to be sent to umpire laboratories. There is also something called as round robin test. So you have to make sure the samples which are there are, even in when the QAQC is done, there are different types of samples. So you have to make sure along with duplicates, there are different check samples also. So wherein you have the exact information from other laboratories also. So again, you have to have a proper control of sampling and analytical procedures. So many times in sampling, it happens that due to contamination, the person who is sampling, he might not be aware what role the contamination plays in sampling. So he might not be cleaning the apparatus or the pad or whatever. So that has to be monitored. That has to be checked. And again, because of core and all I was saying, you have to use special security precautions so that cores and all are not changed from one property to other. And you have to use reliable staff who are experienced in doing this sampling and analytical process so that the data, there is no error in the data. So coming to next, data and data quality, I will hand over to Dhruv, who will continue from here. Thank you.
Thank you, Vikas. So, guys, friends, you understood that till now we have gone through and tried to understand what is data and how important a data can be for mineral resource estimation purposes. We also understood about importance of data validation and how data validation and data collection can take a maximum time of a geologist or a resource estimation geologist in terms of total time that is required for resource estimation processes. Now, I'll take you a little bit deep into the data quality part, and also will try to understand what sort of numeric data are there in which is generally used for mineral inventory estimations. So basically, I'll start with types of samples. So what are the types of samples that are used in mineral inventory estimates? So there are basically, in principle, there are 5 categories of types of samples: point samples, broken ground samples, linear samples, bulk samples, and panel samples. So let's first understand what are these point samples. Now, a point sample is a localized specimen, as Vikas also mentioned earlier, that difference between a sample and a specimen. So a point sample is basically a specimen taken to illustrate a particular geologic or mineralogic feature. A prospector's graph sample is an example of a point sample, can be a point sample. Now, generally it is not representative of a grade and thus cannot be projected from site of origin. Can be an indicative of continuity of mineralization, but it will not be as a good proof for mineralization. Then it varies in sizes. It can come in small sizes, which are called as point samples. Linear samples. Now, linear samples are the most common, particularly samples of like drill core or cuttings, and these are mainly supplemented by other types of samples like channel and chip samples. So basically, samples of drill core and cuttings, as I said, can be a linear sample, and this is the most common sample that is being used in any sort of resource estimation processes. And actually, this forms the main database of most mineral inventory studies. Now, panel samples are other type of sample, which is generally a regular array of collection of regular array of chips. It is taken over on more or less on a planar surface, such as a surface exposure of an ore on the face or the wall of an underground opening, as shown in this figure. Such samples commonly can range from 1 to even to 5 kilograms. Broken ground samples. So these are basically large amounts that can result from trenching and driving of underground openings. This material can be sampled regularly as it is produced, or maybe moved to one or more localities with variable and unknown mixing, possible segregation of by heavy components, even by losses during transit, and also during dilution, because of dilution during sequential moves. Now, a representative sampling is difficult problem here in this case, in case of broken ground samples, and generally require large samples for this. Now, coming to bulk samples, it's basically a very large sample, hundreds to thousands of tons. It is collected. Generally, it's taken to verify the grade estimates, especially in the production sites. So it forms smaller samples or to optimize. It is also sometimes used to optimize ore dressing procedures prior to any mill design and construction even. Now, small scale mining procedures are generally required to obtain these samples. Coming to channel and chip sampling, which is again a linear sample. Now, what are channel samples? Channel samples are those in which all solid material is collected from a long prism of rock of rectangular cross section, whereas chip samples are those in which rock chips are collected at one or more points in a regular pattern along the line in case of a linear chip sample. Channel and chip sampling both channel and chip sampling techniques require access to the rock faces. Channel and chip samples are suited particularly to outcrops or trenches or any underground workings, and generally are taken with the aid of handheld drills. And in this case, uh, of strongly preferred orientation, like if there is bedding, sharing, channels should be oriented across the layering. So that's an example how channels should be collected. So basically, if you are talking about collecting channel samples or chip samples, you have to understand the geology and the bedding and shearing nature of the rock types or the ore bodies where you are collecting the samples, and accordingly you have to plan it and collect the samples. Now, there is a typical problem in channel sampling. Now that is encountered with both channel and chip samples, and it's basically we are talking about preferential breaking of the soft minerals. In channel samples in the rock phases, there can be combination of soft ore minerals or soft gangue minerals. Now, if there is soft ore minerals, then they may be overpresented. They can impose a high bias in on the resulting grade of the sample that is collected. And now, if there is soft gangue materials, then it can get overpresented as which can lead to an underestimation of the grades. Now, such problems can be minimized. How? By taking large samples, where possible, taking separate samples for soft and hard zones, and even weighing corresponding grades by proportions to obtain a weighted grade estimate. Now, coming to concerns regarding data quality. The aim of sampling is to provide value measures. That is, when we talk about assays of metal grades, that are the fundamental information to be used in making any resource or reserve estimates. Now, individual value measures are subject to variability from three discrete sources: the real geological variation, the sampling errors, and the measurement or the analytical errors. Now, the effects of real geologic variability can be dealt with using autocorrelation functions of statistical tools and by the concept of range of influence of a sample. But there can be various types of sampling errors which needs to be minimized, because as we are talking about data, we're talking about quality of data. So importance of sampling process becomes very much important so that we can obtain that quality of data for further resource estimations. Now, there are multiple ways through which we can approach for sampling and data gathering process, so that to maximize the quality of the data and the resulting mineral inventory estimates. Now, the first method, or one of the first method, can be to reduce and know the magnitudes of the errors in the database. Now, how we can do it? You have to plan it for it in the office, sitting in the office. First, you have to plan properly how the samples you are going to collect, or what should be your plan of collection for samples. And then you have to think on also to how you can improve and monitor the quality of assays, and how the representativity of the samples is maintained. That you have to think of and plan accordingly. Further ways to address sampling errors is to develop a sampling plan and procedure that is appropriate for the task. Now, for different terrains, for different geological environments, for different commodities even, the sampling plan can be different. So you have to first understand your requirement, and then you have to prepare and develop a proper sampling plan accordingly, so that you can plan it and ensure that analytical methods and the procedures have adequate precision and accuracies. And also, you should be integrating your geology and the data accumulation and evaluation phases, so that data are obtained and used in optimal fashion with respect to the geological character of the material being sampled. Now, what is the importance of reducing such sampling errors? So first of all, no doubt, minimizing errors. It will minimize errors in sampling. Minimizing errors in sampling and analyzing reduces the very much important effect of sampling, which is nugget effect, that is random variability, and the SIL of the experimental semi-variogram. So this is about how you are controlling your variations in or rather the variance in the sample distribution, using a proper minimizing the sampling errors and using a proper sampling procedure. Sampling procedures that are not optimal introduce an additional, possibly a large component of variance to the geologic or the mineralogic variations. Sampling methods should not be accepted without testing. So we should remember also that we should not be accepting any tests or any analysis without testing them, as methods suitable for one deposit type might be totally inappropriate for another. So that needs to be considered. Often, too little attention is paid to reviewing the implications of the various parameters and procedures associated with the standardized sampling methods, such as diamond drilling, or you're changing the core sizes, or like there are variable core recoveries or variable sampling methods. So these also needs to be considered properly, so that sampling errors are reduced and the sampling process gets high quality of samples. Analytical errors, the same scrutiny as we use for maintaining a quality control on the sampling procedures should be applied here also while assaying practices and results. Reducing the assay variability related to procedural and instrumental deficiencies also improves delineation of old limits and the efficiency of the grade quality control during production stages. Design of optimum subsampling procedures can be guided by G's sampling equation, which is a sampling which is given by G which is called as G's formula or G's equation in sampling theory, to appreciate inherent errors and to minimize the nugget effect. Reports of assay results should contain information about sample preparation and analytical methods, including information about detection limits. Now, this is about G's formula. We have not covered much here in this lecture, but if anyone wants to know further about G's formula and about sampling theory, you can connect with me and I'll share something for that as well. Now, a very important part of any sampling procedure or any maintaining a proper data quality is the location of sample. Now, this is a critical aspect in data quality for resource estimation. It's a myth that sample locations in space are well known. Sample sites and drill collars must be surveyed for accurate positioning in 3 dimensions. And because drill holes wander, and depending on the orientation and the physical characteristics of the rocks where the drilling is going on, or where whatever rocks they are intersecting, drill holes wander, drill holes deviate. Now, even a small deviation from a planned orientation at the collar of a hole can result in substantial departure of the end of hole from the planned positions. Now, to explain it or make you understand better, you can look into this example in this picture. Now, this problem is illustrated in this figure, in which there's a small progressive change in the plunge of the drill hole, 1 to 3 degrees over 50 meters, and which resulted in the end of hole being shifted about 30 meters from the projected position. So that's why identifying the location of sample, doing a proper drill hole surveying is very much important, along with collection of sample for resource estimations. So if you want to conclude, a drill hole must be, for the location of samples, a drill hole must be surveyed at intermittent locations along its trades. And this information is then combined with the surface information, collar coordinates, to determine the realistic 3-dimensional coordinates for samples along the true drill hole traces. Now, coming to the error classification and some terminology. So we'll go through some terminologies which are used while classifying errors. First is accuracy. The accuracy of a sampling and analytical procedure is a measure of how closely the true value of the sample is approached by reported analysis. Generally, true values are not perfectly known. So what can be done? Follow a procedure that provides a close approach to true values of samples, fundamental to the method in the availability of a compositional range of standards that are widely analyzed by a variety of proved analytical methods and whose mean values are well known. These mean values are accepted as the true values and are the standards used to calibrate other samples. Bias. Departures from true values are called bias, a matter that often receives too little attention and yet is normally the most significant source of error in economic terms. Then comes reproducibility. Reproducibility is nothing but precision, which is a measure of the inherent variability of a specified sampling and analytical procedure and need be a little similarity to accuracy. For example, a particular acid extraction of copper may not attack certain copper bearing minerals and thus may underestimate copper, even though repeated analysis give very consistent results. Now, other than that, there are some other definitions like random errors, coefficient of variation. Now, random errors in general, when only random errors are present, the error can be summarized as an average of variance or as a standard deviation, which is relative to the mean. Now, commonly for coefficient of variation, the relative error as when you is described as percentages, and the quantity like the standard deviation upon mean is also known as this coefficient of variation. Now, precision, as I already talked about, precision is a quantitative measure of reproducibility, commonly is quoted in terms of two standard deviations as a percentage of the mean. Now coming to sampling patterns. So traditional sampling patterns are random, or they can be random stratified or regular or irregular. Now there are all the four examples are shown in this image of like random sample locations with the field V, say V, and then the B image is showing a stratified random sample, which is with each of n samples located randomly within a small block of V, small v within a field, say capital V. Now the third option, C image, is showing a regular sampling pattern where samples are located at the nodes of a regular grid with the cells summing up to total of that area. And then the fourth one is the clustered or the bias sampling pattern. That is, the sampling is not representative of the complete box. Now approach what to do for sampling patterns in mineral estimations. An important element of this approach generally consists of orienting the most dense sampling direction perpendicular to the plane of greatest geologic continuity, as estimated from the geologic model at the time of sampling. Such a strategy can lead to several pitfalls also because of the assumptions involved. Thus, continual review and refinement of the sampling strategy is required as you understand for the geology and the assay knowledge from time to time. All regularly spaced sampling grids are subject to the possibility of strong bias because of periodicity in the sampling field. This problem is particularly serious for widely spaced exploration data. A general problem in all cases of estimation is whether sufficient data are available for the required estimates or not. Sometimes obtaining additional data may be desirable, and even sometimes it is necessary as well. Now, to make you understand further about the value continuity, how the value continuity varies in 3 dimensions. Now, if you see here in this image, where I've shown a 3D image where drill holes are drilled in each sections. So sample points or intersections commonly are far more widely spaced in the horizontal plane if you see in the strike direction. Thus, the detailed determination of continuity that is obtained with relative ease and assuredness along the drill hole axis is not readily obtained in the other 2 dimensions. So here you can see in the drill hole sections, the continuity of the confidence in the continuity of the samples is more rather than in other 2 directions like strike or in the widths. So in such cases, physical or value discontinuities that are shorter than the drill hole grid cell may be missed, particularly where actual rock exposures are sparse or absent. This can be further understood by this variogram, where I have shown 3 variograms, the variogram, semi-variograms in 3 directions rather. So for a copper deposit in Huckleberry porphyry copper deposit, and the downhole composite samples are spaced. If you see the downhole composite samples, the vertical one, you are spaced about 8 meters apart, whereas the horizontal plane samples are mostly at 6 to 8 times as far apart. Now, clearly the autocorrelation, which is a semi-variogram model, is not well known for the short distances in two of the three principal grid directions. So this is a situation that could be reflected by gathering appropriate and closely spaced data during exploration. And that is quite critical while doing estimation to improve confidence in other two dimensions as well. Now, coming back to sample and sample collection processes, how the sample reduction procedures can improve your sampling process. Sample reduction or subsampling protocol is the totality of the procedures that are used to extract a much smaller representative amount for actual analysis from a large sample volume. A mineralized sample commonly is a mixture of relatively large but variably sized fragments of solid material that must be reduced in both particle size and weight to a small amount of finely ground material that is analyzed to determine metal content. Now, this overall procedure known as subsampling protocol involves a series of steps of alternating particle size reduction and mass reduction that can be demonstrated by a simple, purely illustrative example, which I have shown here. Like, say, for example, suppose that there is a sample consisting of 1 meter of half core, which is weighing somewhere around 2,700 grams and consists of fragments up to, say, 10 centimeter in length. The sample might be crushed so that the maximum particle diameter is, say, 0.5 centimeter. Then the crushed material is homogenized and a portion is taken, say, 1/4 of the original sample, perhaps by riffling process. Then this smaller portion is then further crushed or ground to a much smaller particle size. And again, the material is homogenized and a fraction is taken, perhaps another 1/4 of that material. Then the remaining 3/4 of the material which is left at this stage might be saved as a reject, which can then be used for further reanalysis or further validation of the process. So that is how the samples are reduced in a step-by-step process. And then the rejects are used as the unused pulp or the fragments are retained and used later on for rechecks or for checking the analysis again. Coming to assay quality control procedures, a quality control program is necessary always in order to know and to monitor the variations in the data quality. For this purpose, the concept of an analytical system is useful. An analytical system is composed of these three factors, like the set of samples with the analyte is in a specific matrix, the exactly defined analytical procedure, and the particular instrument that is used. Now, laboratories usually maintain a system of checking for subsampling and analytical errors. This normally involves periodic reanalysis of internal and international standards. Companies also use various quality checks for assurances of the sampling and sampling analysis obtained from the lab. But we are not discussing today further in this because it's in itself it's a long chapter, and maybe we will be taking a proper quality control on QQC, a different lecture altogether later on. So for today, we just understood that assay quality control procedure is important, and there are various methods of applying checks and applying quality control procedures so that we have a proper assurance on the analysis. So that's all which we have here for you today in this data and data quality. And let's try to summarize what we have gone through. So we started with data collection, understanding data collection, the chain of custody, data validation, and how to read data. Then we have gone through the implications of data quality and difference between sample and a specimen. We also try to understand what are deliberate errors and how we can rectify them. We also gone through the types of samples that are used in mineral estimation. We understood the major concerns regarding data quality, understood sampling errors, analytical errors, and ways to rectify them. And then we also have we have seen the importance of a location of a sample. And finally, we have gone through the sampling patterns, sample reduction process, and the role of quality control procedures. Now, let's conclude with these key takeaways for your future work, or whenever you went on field and collect, or you start a sampling process or a sampling program. Data acquisition process may not be of adequate quality to properly represent a mineral deposit, or in particular case to properly define the geologic and the value continuities on which mineral inventory estimates depend. Now, for high quality resource reserve estimation, high quality of the database can be maintained by systematic critical evaluation of sample acquisition, which includes three-dimensional aspect of deposit sampling patterns, then sample reduction and assaying procedures, and understanding the geologic data acquisition, interpretation, and modeling. Now, third point is sampling patterns and methods, sample reduction schemes, and assaying procedures must be designed and tested for the local geological substrate. Then finally, a regular program of duplicate and check sampling and analysis serves as a continuing measure of a quality control. So that's all we have today for you all in data and data quality for mineral resource estimation. I hope you have you have liked it. And so that's, if you have any questions, you can ask, or you can put it in chat box, and we will try to answer it. And before that, I just want to mention you about what is there next week. In next week webinar, it's a special webinar which we have started last month, which is called Partner in Progress, and it's the second webinar which is going to happen in this series, and where we call our eminent speakers, international eminent speakers. And next week we have the topic on recovery of rare earth elements from secondary resources, which will be given by Dr. Huck, who is from Australia. He is a professor there, and he's working in the energy sector. So for today's topic, that's all I have. We both have, and if you have any questions, please put it on chat box, and we'll try to answer. So I'm allowing mics as well on now, so you all can, if you have any questions, you can unmute and yourself, and you can ask questions as well.
Good morning, sir. This is Anirban. The presentation was really good, and I liked it a lot. And I also think that, as you have said, that as a quality control procedure, if there will be some presentation or webinar on that, I would like to attend. Maybe for different commodities, that will be good to learn on that aspect. And I have learned a lot from this presentation. Thank you. Thank you to you and yes, sir.
Yeah, thanks, Anirban. Anirban, we also, whenever any presentation or any webinar that we will be conducting, we'll keep posting them on our LinkedIn or on our Facebook page, so that if you are following us, you might come to know, or if at all you want to directly message us, you can message us also. So we'll be glad to let you know when we are doing it.
Sure, we will be doing it, because if you all have gone through the earlier two webinars also. So basically what we are trying is we are trying to subset the mineral resource estimation procedures in multiple webinars. So which we started with an introduction on mineral resource estimation. Then we have covered some essential concepts in mineral resource estimation. And then now we have gone through this data and data quality. So next two topics which I can infer right now is one will be QQC, and another one will be to give you an indication on what are the different types of resource estimation procedures that are there. So hopefully we will cover it soon.
Mr. Nath.
Yes.
I'm CV Rao, ex GM ONGC.
Yes, sir. Hello, sir.
Hello, sir.
Yeah, I met you in SPG, I think. Okay.
Okay.
Actually, presentation is good, and you covered many of the topics on data part. I would like to know any process automation in this particular data handling part.
Process automations are there. Basically, if you see, it's a part of data analysis, a way of data analysis. So there are tools like in any software packages, there are tools which is called exploratory data analysis, which is there in various estimation softwares, be it Datamine or Subpec. But if you don't have Datamine or Subpec, then also you can do such analysis in Excel, and there are formats which are there to generate charts. I can also mention some of the very good softwares which are there in internet as well, like Tableau or Power BI, which are also useful while using the analysis part of the samples and identifying. But the basic thing is you have to understand that what are the charts or what are the parameters you want to extract from.
Yeah.
And
actually, my point is because when I have never dealt with mineral data, only before ONGC I was working in GSI. I have some mineral exploration.
Yes, sir.
Whereas oil exploration, we have big data, and we'll go for the automation principles in any place.
There are methods.
Maybe not that much big. So
yes.
That's why I wanted to ask you.
Yeah. In fact, people are. Thank you, sir. In fact, people are working on machine learning as well right now these days. We also working on research. We are doing a research R&D program with Minex CRC, which is an Australian research organization where we are working on it. And we have research team who are working and trying to do the analysis part using machine learning. And there are various tools available in the online platform as well, but ultimately it's data analysis, and
you and the Karunakar and team are the authority in mineral, and be as the authority. All the best to you. Thank you.
Yeah. Thank you.
Thank you, sir.
So thank you, guys. I think it's almost 12 now, so we will be closing it. And please, we will be sending the webinar link. I think it's the webinar link for the next partner in progress topic is also there in our website. So please go through it and register. I'm sure that live webinar is also going to be a quite exciting one, because rare earth critical minerals is quite a hot topic right these days. So please do join there also, and very good afternoon to all of you. Thank you.
Thank you, everyone.
Thank you, sir. It's a nice and very interesting subject to us and learning.